Okay, so we can start. Hello everybody, my name is Avi and I'm Technical Marketing Manager for EMEA in Mellanox Technologies. First of all, thank you for joining this session. I'm not taking it for granted. There are big competition doing some session, Arista and Cisco. So thank you very much for that, for your interest. First of all, before I start, I have a question. Who is familiar with Mellanox here? Whoa, that's pretty good. That's pretty good. So just an overview for those who are not familiar with Mellanox. So Mellanox is a company that was established in 2000, and it started in the HPC industry actually. So we have really huge customers. I can mention some of them, NASA, for example. So I probably said the biggest one, or SKA, or CERN, or many big universities. And the principle of the HPC market, high-performance computing, is that on the network side, you should not lose packet, you should be fair, you should bring high bandwidth, you should do low latency. Now, those seems like, kind of trivial concepts, but on the Ethernet market, they are not. And what Mellanox is doing for the past 7 years is basically bringing those concepts into the Ethernet market. So it's a bit old slide, we're near 3,000 people worldwide, and we're closing this year close to $1 billion, and we are public. So this is Mellanox, and what I will do now is I will describe our unique solutions, but I will do that first, starting with showing one of the biggest demands in the market, and then our building blocks, because I think unique solutions comes better if you have unique building blocks. So there are many demands in the modern data center, but I will focus on one that we are pretty good at, and this is the high bandwidth. So why do we need high bandwidth? So first of all, each one of you guys probably is using Facebook, Twitter, LinkedIn, is uploading dozens of pictures a day. Some, I'm personally not, but some people are. So we are creating a lot of data, and this is only us. There are people around the world, a lot of people that are doing that, enterprises. And it's not only about creating a lot of data, it's also about fetching it faster. So what happened in the storage industry? What happened is that storage become much faster. To utilize a 100 gigabit link, you would need 250 spinning disks. If you are moving to flash SAS SSD, you only need only 10. With NVMe, if you have only 3 cards, 4 actually, basically your network becomes a bottleneck for 100 gig. I'm not talking about 10 gig. This is 100 gigabit Ethernet. Also, what's happening is that the industry is moving to cloud. What does it mean, cloud? Cloud means basically that we are moving from a scale-up technology to scale-out, or pay-as-you-grow, all those, saying. And it means basically the traffic that was in the past moving from south to north now is moving east to west. This is especially happening in the hyperconverged technology, because you have compute and storage everywhere now. Everything is everywhere. And traffic is now moving east-west. So even if you take 10 ports of 10 gig, and you have a network that is as a leaf spine topology. If you're taking 10 ports of 10 gig and you're pushing now one big file to another target, you are basically utilizing 100 gig between your leaf and spine. So we will bring high performance and high bandwidth. But the problem with new feature and advanced feature, cutting edge feature, is that most of the time they are adding complexity. And to reduce complexity, the best way to do it is, first of all, make sure that everything is in-box. Everything is easy to configure. You don't need to do much. It's just there. Okay, you're connecting a port, you have 100 gig, everything is working, fine. So one of our advantages, specifically, and I will focus on VMware, not other cloud infrastructures, but we also have the same concept in others, is that we are doing integrations with VMware to make sure that all those speeds are in box drivers. And also, if you have nice features like Rocky that I will talk about later, they are all standard. And they are also our solution. And to make sure that everything is and management and is manageable and monitored really well, we also have a management tool that I will mention later on, which is called Neo. So I will start with the building blocks. If I would try and say what are the 3 big advantages of Mellanox versus other network vendors, is that one of them, we have the end-to-end story. What does it mean end-to-end? Actually in 2 dimensions. First of all is the horizontal dimension. It means that basically we are doing NICs, cable, switch, cable, NICs. So from PCI to PCI, we're doing everything ourselves. And it means more than just, for a customer that he could buy from us the NIC, cable, and switch. That's, we prefer if you do that, but, and we are not, by the way, we're not locking anything. You can choose whatever cable, you can choose whatever cable you want to choose, or whatever NIC you want to choose. Probably you choose Mellanox NIC because we are above 10 gig, 95% of the market. You can choose, but whatever NIC you want. But more than that is that we kind of understand where exactly some features should be, what exactly the concept of those features should be in each of those parts to make sure that you can run 100 gig. Because, buying equipment that is doing 100 gig and put it and connecting it, you will not get 100 gig. It will not happen. I can promise you. Okay? It will not happen. The only way it will happen if you will use some of the things that I will show next. So this is the end-to-end, but it's not only end-to-end when it comes to, NIC cables, switches, cable NICs. It's also end-to-end when it comes to the system itself. So basically, Mellanox are doing the silicon itself, the box, and the software. Everything is done by Mellanox. And the silicon is our 3rd strong advantage. We're doing our own silicon, and it came from the concepts that I talked at the beginning from the high-performance computing. So I will show some slides about comparing our silicon to the merchant silicon, the most common one, which is the Broadcom one, some benchmarks that we did, and I will show you some differences between those 2 silicons. And also the same on the NIC side. So on the NIC side, it's called ConnectX-4 or ConnectX-4LX. We're doing now ConnectX-5. Those are 100 gig capable NICs. So they basically, when I'm saying 100 gig capable, it means that you can do from 1 gig to 100 gig. It means 1, 10, 25, 50, 40, and 100. Also, the Spectrum, which is the silicon for the switch. And on the system of the switch, we have basically, on the line, product line of the Spectrum, which is based on our Spectrum silicon, we have the 32 ports of 100 gig. It's, no, there are other switches in the market that look the same, basically. I'm talking on the system level. We have the 48 ports of 25 gig or 10 gig. It's the same form factor. It's called SFP or SFP28. It's the same form factor. It means that you can plug your existing cable and get 10 gig from it. Or if you plug it SFP28, you will get 25 gig from it. And I will explain why we think that 25 is the new 10. But anyway, you can get from here, from the uplinks, 8 ports of 100 gig. Okay? Or 40 if you like, but we don't see a reason why not go with 100. And this is a unique product on the system level. There is no such product in the market. Actually, this product, we are the only one that came with it until, last month, I think, or 2 months ago. Then Cisco joined us with such a product. But this one is really unique, and you will not see it in the market. And this is basically half a switch. It's 16 ports of 100 gig. Why are we the only one that are doing it? For the simple reason, because we are doing the silicon. If you're taking another vendor, he needs to pay on the silicon the same money that he pays for this one. It doesn't mean a lot for this vendor if he's doing this size or this size. So he's paying the same money. Because we are doing everything, we can make it cost effective, because from the end customer perspective, he's kind of saying, okay, this is half a switch, so I want to pay half the price, kind of, okay? So this is the main reason that we are the only one that are doing it. Actually, we did it also in the legacy product line, and nobody else did it, so this is why I'm so sure it's unique, and you will not see it in the market. And what's so special about 16 ports of 100 gig? Here's the use case. It comes, let's say that you have 40 servers of 10 gig in your rack. It's kind of a medium, large rack, I think. And you need to have high availability on the top of rack. So it's quite, a dense rack. You need 40 ports. So basically, you are taking 10 ports from this switch and splitting them by 4. This is a split cable. One side is QSFP. This is 100 gig or 40 gig. And this side is 4 ports of 25 or 10 gig. So if you are taking 10 ports, splitting by 4, you basically have 40 ports of 10 gig. You are connecting all your servers here, 40 servers here. Good. For HA, you need something that's called MLAG. If you are doing layer 2, this is usually what's happened on the top of rack, or you can do layer 3 or whatever, but usually this is what happens. So you need 2 ports. You're taking 2 ports of 100 gig, and you are connecting those switches together. MLAG is not something unique for Mellanox. Everybody is doing it. Cisco is calling it VPC, Arista MLAG, JLAG, whatever. So we took 2 for the interconnect. We took 10 for the servers. We are left with 4. But those are 4 ports of 100 gig. It means basically to the spine layer here, you are pushing 400 gig up and 400 gig down. So we are non-blocking in this size. So in 1 U of the rack, you spent only 1 U, 94 watts, the lowest in the market. Basically, you have everything that you need for your 40 servers with HA in this size. And this is what makes this product unique. And there are other use cases for this product. We have our Nutanix guys here, so we have a nice solution with them. Basically, this is a great product for Nutanix or other software-defined storage companies. But this is only one use case. Now let's move a bit about the software. So we have the story in Mellanox of being open. What does it mean being open? So first of all, we are part of OCP. That's great. We took our MLAG. Remember the proprietary protocol? We put it on GitHub. We don't care. People can do it themselves. Microsoft came to us and said, OK, I want to run something that is called Sonic. This is a network operating system, and I would like to run it on your silicon, but also on Broadcom, because I would like the option to switch the silicons. But the problem is that to do that, how the switch works, basically you have the silicon here, and you have something that's called SDK that is controlling. You have a software that's called SDK that is controlling the silicon. We have our own SDK. Broadcom have their own SDK. So for Microsoft, it means 2 codes. One of them will control through the APIs of Broadcom. One of them will control through the APIs of Spectrum. And this is not good for Microsoft. So what we did with Microsoft, we created something that is called SI, which is basically an abstraction layer here that is similar to Broadcom and Mellanox. So Broadcom must jump into this wagon, and they did it. And today, Sonic can run over Spectrum, over something that is called SI. Oni is kind of a pixie boot for switches. It allows us to work with many, many network operating systems. Basically, it means that you are putting your image on the HTTP server, and you can run Mellanox OS, which I will talk in a second. This is our OS, or switches to Cumulus Linux. And Cumulus Linux is the latest operating system that we offer on our switches, and I will touch it in a minute. So this is about the operating systems, and about the silicon itself. What we basically did for the third time, we did some comparisons with a company called Tolly. This is a third-party company which is doing benchmarks. And we took the Broadcom Tomahawk and the Spectrum silicon. How we took the Broadcom, by the way, we just bought a Cisco 3232C. We are buying every significant product in the market, and we are putting it in our lab. I'm sitting close to this lab, so I'm familiar with it. And we are not getting any discount, believe me, from Cisco. So we bought it, and what we did basically is took it to Tolly, and Tolly did the tests. And We saw similar thing to the previous test that we did at Trident 2 and other silicons for Broadcom. We saw that the Broadcom is losing packets. They are losing packets in small packet sizes. And that's bad, but it's not worst thing in the world. A network can live with such a thing. There will be some retransmissions in the control path and so on. Okay. Another problem that we saw is that, and again, this is a known issue, is that we are doing a constant latency of 300 nano in this product, but with the other silicon, it starts with 500 and grows as the MTU grows. It can reach to microseconds. But what most surprised us was this part. And this part is critical for the network, especially for the cloud. It means basically that if you are choosing some ports on the Broadcom silicon and choosing some ports on the Spectrum silicon and creating congestion on them, if you are choosing the right ports, you will see that everything will be split equally between those ports. But if you are choosing different ports and you cannot really choose, you will see this phenomena where one port that is congested will get a lot of buffers, a lot of the buffer, shared of the buffer, and the other one will fight for the rest. But Broadcom is saying they are doing shared buffers. We also say that. It's 16.6 megabyte. But the difference is that Broadcom are doing actually 4 cores actually, of 16 megabytes. It means that you have 4 megabytes for a group of ports. So if you are choosing 3 ports on this buffer and 1 port of the other buffer, this one is getting the entire buffer for himself, the 4 megabyte, but those one are fighting for the chunk of the buffer that they are using. And this is a big difference. We are not the only one that are talking about it. Also Cisco are doing it because they invented their own silicon that is called ASE2 and 3. And they're saying the same thing. It's public on the website. So in general, I would say that our strong point in our products is our silicon, which brings, we are not losing packets, we are bringing low latency, and we are fair in the network. And this is explanation about how the buffers work with Broadcom and Spectrum. And when I'm saying Broadcom, basically I'm saying Arista, Cisco, Brocade in some products. Most of the products today are based on Broadcom. Okay? Now we'll move to some of the features that we are presenting, and actually we presented in the VMworld 2016. So we have great building blocks. Maybe, you can agree or not, but let's say that we do. As I said, first of all, we introduced the 25 gig to VMware this year. So it's with our drivers and it's in box on the vSphere 6.5. And this is very, very important. I will touch why 25 gig can be good. We also have first ever support of RDMA Rocky, basically Rocky RDMA over converged Ethernet in VMware. I will touch that also. Nice solution when it comes to storage, vSAN, and VMU over Fabric, which is exciting. ICER, I will not get to all those protocols, but I will touch some of them. And also, I will talk about offloads on the next slide. So let's start with 25 gig. Why 25 gig? Why not? Basically, if you are building an infrastructure today and anyway you are using the same 4-factor SFP or SFP28, it looks exactly the same, and you can use 25 gig, it can help you in many, many ways. This is one example. This is an NVMe drive. You remember the slide at the beginning? I said that with 4 NVMe, you are utilizing 100 gig. So actually, for one NVMe flash drive, you need 3 links of 10 gigs. And this kind of equal to 25 gig. It will give you the same results. So you can just, do your cost calculation. You can save the number of ports. If looking at the VDIs, you can see that with 25 gig, you need less servers, okay? Because you can run more virtual desktop per server. And eventually it comes to the cost. So with 25 gig, basically you are getting more bandwidth on the same form factor, and now it's available on VMware. Another use case that I would like to mention is the VM migration. This is a comparison between 40 gig to 10 gig. I don't think we did 100 gig yet, but I think you can see the idea behind this. Doing a faster and accelerated networks mean that you can do VM migration much, much faster. And in a nutshell, it's mainly because there is a race condition between the movement of the data from one VM to another during the VM migration to the fact that the VM can be populated with more and more data. And since the storage become much faster, as I said, there is a race condition. So eventually, from the test that we did, you see there is a huge difference between using 10 gig or 40. And you can think about the same for 25 and 100. Another point, as I said at the beginning, because we are doing end-to-end, we kind of have an idea where exactly to put the feature to make sure that you can really run 100 gig or 25 gig or high speed. You can really reach those numbers. One of the obvious examples is the VXLAN overlay challenge. So, what is VXLAN? People sometimes forget it. VXLAN is UDP packet, okay? If you are putting a NIC, a simple NIC on a network that doesn't know what it is, it means that once a VXLAN packet will reach the NIC will just look at it and say, okay, whatever, and will push it up to the stack, to the software. Once you are hitting the software, the bandwidth reduced dramatically. You must keep the traffic on the network on the fast path, which is the hardware. So what you need to do, and this is capability that Mellanox provides on NIC side, is you need your NIC to be able to go deep and peel the headers, the outer headers of the VXLAN and go to the encapsulated frame and read it and do simple operations that are being done on a VLAN. For example, checksum, RSS, TSS. Those operations cannot be done on the hardware level if you don't have this capability on the NIC side. And this is, in a nutshell, the idea behind the end-to-end. It means that most of the offloads, most of the acceleration features will happen on the NIC side. You need good cables to maintain the speed, and you need a switch that will maintain the speed. It needs to be fast, it needs to not lose packet, it needs to be fair between all ports, and it needs some features sometimes, and we touch it. But most of the offloads, when it comes to bandwidth and performance and accelerations, will happen on the NIC side, and this is one of them. And you can see some measurements that we did. This is connecting 3. We advanced from there. Actually, it connects 4 family. Okay, so this is 100 gig or 40 gig, but we did this with, I think, with the 40 gig. Yes, with the 40 gig test. And you can see those graphs show this is a physical server doing VXLAN. Sorry, this is physical, VLAN, just VLAN. And this is the VXLAN offload. So we're very, very close to the performance of the VLAN. And this is, again, this is because the NIC is doing the same thing that it's doing with the VLAN, the same operations. And without offload, the bandwidth reduced dramatically, as I said, because the hardware is not doing this job. And what happened is that this is the CPU. And this is important because, as I said, once the hardware is not doing the job, so someone needs to do it, and this will be the CPU. And the CPU is not for network. It's for applications. And this is our main idea. And talking about CPU for application and network for network, I think this is RDMA Rocky is the most generic thought about how network should work. And RDMA Rocky, when say RDMA Rocky, basically you are saying Mellanox, there are other vendors that are doing it, but we are kind of leading this idea and the market of the NICs in general. But basically it means that on the traditional way of network, to basically copy memory from one machine to another, you need to go through the TCP stack. Okay, so you need to go through, let's say, for the bare metal on the kernel. And again, if you are involving software, you are in problem. You cannot really reach high bandwidth. You can do it. Actually, we're pretty good in doing TCP IP in high bandwidth. But the easiest way and the fastest way will be actually RDMA or Rocky, which is RDMA over Converged Ethernet. And the idea basically is that the buffer on the application is connected directly to the NIC. It's called the QP, actually. Actually, there are pairs of queues here. And the idea is that the NIC, the hardware, is getting direct access to the application memory and copy this memory and just move it to the other system. okay? And there is no need for the TCP/IP stack to be involved in that. And it's responsible for everything that TCP/IP stack is doing if there is a need for retransmission or, of course, the movement from virtual memory to physical memory addressing and so on. Everything is doing by the capabilities that we develop over our NIC. By the way, you can do RDMA also on the software, but it doesn't mean anything. Basically, you are not doing anything. This is bare metal. To talk about Rocky over with VMs, there is something that's called SR-IOV. And basically, you need to do the same thing, but the way to do that, you need to actually give the VM some function to work with, and this is called virtual function. So actually, there was the way together was at the beginning. There's something that was called emulated device, which was fully emulated on the software, and then Power Virtual, which is part of the software and part of the hardware. Hypervisor was responsible to provide, the function, and there was also a pass-through where basically you are providing the VM the physical function, the actual port, but this is a problem, it's not scalable. And the last solution is SR-IOV, where basically we're taking the physical function and duplicating it many times, up to 250, basically providing each VM virtual function, which is the physical function itself. Okay, so this is the idea. The problem with SR-IOV is that it basically bypasses the hypervisor completely, and by doing that, you are losing many of the advantages that you have on hypervisors on the control plane. Just one example is OVS, for example. You don't have it. So you cannot do, for example, VM migration and so on. So this solution is mainly for developers on the kernel level for services. Before I will touch one use case for using SR-IOV and RDMA, I will show you some numbers. So you can see here the numbers of latency versus TCP versus RDMA. So RDMA are here. This is the RDMA read and write. This is TCP. And when it comes to bandwidth, it's kind of the opposite. This is the TCP here. Bandwidth is lower, and RDMA this is 100 gig. One use case of using this technology, it's called NVMe over Fabric. NVMe, if you're not familiar with it, I guess you are, but basically it means cutting off old plugins that were relevant for spinning disk and other technologies, and basically bypassing them to make sure that you have very fast flash storage. But this is local on the server. To make it over Fabric, you need the same technology for the network, and it's called Rocky. This is exactly what I mentioned on the network side. So basically, NVMe over Fabric is powered by Rocky, and there is a company called Maxtor, but there are also other companies, and they showed very advanced performance numbers doing NVMe over Fabric. So this technology is nice, but it's mostly for services, and VMware and Mellanox work together to get to a concept called PVRDMA, or Power Virtual RDMA, and basically it's get good things from both worlds. It's, again, the data plane is going directly to the NIC, but the control plane is still on the hypervisor. So basically you can enjoy all the control plane benefits and have a good performance on your data plane. And one good example for that is VM migration. So you can do it via RDMA, I think from 6.5, I'm not sure, but I need to check it. But anyway, very soon you can do that. And actually, if you have some servers, VMs, that are working still TCP, you can do both. So it's not kind of choosing how to go. And this is some performance measurements for 40 gig for PVRDMA. And you can see here again that there is a huge difference between, on the bandwidth and latency between a PVRDMA and the plain TCP/IP. On the control plan, we are providing with all our switches a product that is called Neo. It's come for free, by the way. And the idea is that we are providing a tool, a GUI tool, which also can be integrated in vSphere from, I don't remember exactly, but for sure 6.5. Some of it can be integrated. The reason it can integrate it easily to vSphere or to Horizon or to whatever a product is because it's basically our GUI that we are providing is built on REST API, and other monitoring system can just integrate this REST API to their systems, and you can have one pane of glass. And Neo basically what it's doing is controlling, provisioning, and monitoring our switches. Not only our switches, it can also monitor other switches at some level. But provisioning is mostly our switches, Cumulus or Mellanox, it doesn't matter. And it can provide nice view of the network connectivity that basically it's doing LLDP, knows exactly how the network is connected. Some graphs showing hot spots and hotspots is something that you will decide what it is. It can be high CPU on a switch, it can be congestion, it can be alerts on the level of a threshold that you decide, whatever. Also some counters and so on, and give you basically visibility on the network, which sometimes is the piece that is missing when looking at the entire software-defined something. Okay, so if talking about software-defined storage, for example, or cloud, network is kind of sometimes neglected. Companies that is doing software-defined storage will probably say, okay, you will use our tool, you will do 1, 2, 3, 4, 5, connect to the network, 5, 6, 7, 8, and everything is working. The part that is connect to the network, it's not very trivial, and you don't really have visibility on it. And this tool is kind of completing the visibility of the network also for other solutions. So if I will try to summarize what basically Mellanox is providing, I took this SDN concept, and usually I'm looking at EMEA. Usually when people say SDN, in most of the places they mean overlay. And what we are saying is that we are providing basically the capability of offloads and acceleration on an NIC side to make sure that you can run the speeds that you would like to run. If it's 25, 50, 100. And we are also offering VTAP on the switch if you would like to terminate your VXLAN on the top of rack if you are connected to the bare metal. If you would like to do it on the hypervisor, you can also do that. There is a nice feature that is doing OVS offload on the NIC side. It's not available yet from VMware, but we will work on it. And basically, we have the entire solution for your network when it comes to SDN with the completion of Neo, which is the monitoring system. You can use Cumulus on your switches, and then if you are a Linux guy and you really like the concept of Linux over your switch, you can use Cumulus and enjoy the powerful things that Ansible or Puppet can do. The same modules that are used to, that are working for the server can also work for the switch side. So you can use the same modules and it works great. This is basically Linux Debian running on your switch. If you don't like the concept of Linux on a switch, actually Cumulus Linux came also with the CLI now. So there was always a CLI for the layer 3. This was basically Quagga, but also there is a layer 2 CLI now. But if you like more the traditional concept of an OS, we have also the Mellanox OS, which is kind of a GUI, CLI, SNMP operating system equivalent to other operating system, Nexus EOS, or it's kind of the same idea. I talked more over overlay, but we also support OpenFlow 1.3, so we also offer that. And I will complete my session with the use case. A cool company. I chose this company, you know what, because it wasn't the easiest one, but I think because it was challenging, it was a nice deployment eventually. So CloudAlyze is a company that is doing GPU desktop as a service. So they need a lot of bandwidth in some places, and they also have some connections that are lower bandwidth. So they have everything basically. They have in some points they have end-to-end 100 gig from the NIC card. There's 2 ports of 100 gig up to the leaf and spine. Some of them 40 gig, some of them 10 gig. And with our products, we can just offer a product that can do all of those speeds. So they can choose exactly how to connect their servers. If it's 40, 100, everything is backward compatible and future-proof. So for example, If they are buying, QSFP cables and connecting it today, 40 gig, they can move easily to 100 gig when they want to do that. And they can use their old cables. They are doing 400 gig, connect them directly to the switches and enjoy the 40 gig. They're running Cumulus over the switches, and they are using Ansible to orchestrate the entire fabric. They're using the VXLAN offload on the NIC side, so this is why they can really run this kind of a traffic. They're thinking about Rocky, not there yet. Rocky is a more cutting-edge advanced technology. It's more complex also to develop, but this is a plain TCP/IP, so they can run 100 gig with the ConnectX-4 and the offload capability. The offload capability, by the way, it's one parameter in the driver. That's it. Okay, you just decide that you want it and you have it. It's the whole idea. And the switches here are not doing anything than just the switch should do. So they are doing here MLAG, which is the layer 2 protocol that I talked about, the high availability, and layer 3 between leaf and spine BGP. Okay, so it's a kind of usual configuration for a scale out. And they are paying as they are growing. It means that they started small and they are adding, and they will continue to add more and more leafs. And once they don't have enough ports here, they will add more and more spines. And this is the idea basically that industry is going to, because you should not basically buy huge chassis switches, pay a lot of it, but not use all the ports on it. You can today basically pay as you go, as I said, put more and more switches as you grow. The only challenge is for this paradigm is that you need to somehow manage it. And this is where Neo come, and Neo can help you provision this architecture and also monitoring it. And you can use, as I said, also the native Linux tools like Ansible, Puppet, and so on to do the same job if you would like. Yeah, so this is and they're using, of course, VMware NSX. At the beginning, and this is what I wanted to say, at the beginning what happened is that we didn't have the VTAP functionality on the switch. So there was a problem because there were some bare metal servers connected and they needed VTAP on the switch. VTAP, by the way, I'm just saying VTAP is the termination of VXLAN, and it's doing layer 2 or layer 3 gateway, but we are doing layer 2 gateway, so it's a layer 2 gateway. It's for bare metal, it means that it matches the VNI to a VLAN, so bare metal can participate in this part. It is called overlay. So VTAP was not on the switch, so what we did basically, we just put it a couple of very strong servers, put it our NICs there, run the gateway NSX on those servers, not on the switch, and we got the same performance. So we kind of worked with this company, even we didn't have this feature yet, we worked with the company to make sure that they're getting the functionality that they need, although we don't have this feature. And the reason we can do that is because, again, because of our view of how end-to-end network should work, the offload is happening on the NIC, most of the offloads. So you can use our NICs to do sometimes things that the switch needs to do. But anyway, by the end of the year, they will move here to VTAP on the switch, so everything is okay. Any questions?
You were showing pretty impressive performance numbers on the NIC.
Mm-hmm.
And so how much can you actually push across a single PCIe bus?
So it depends what kind of a PCIe bus you have. So you need Gen 4 basically to push 100 gig, I think. So yeah.
Gen 4?
Yeah. Otherwise you cannot, you need a strong server to push.
You top out at around.
Mm-hmm. Yeah. But what you don't need, if you're using RDMA, for example, Rocky, what you don't need is a powerful CPU. Actually, you can use a very, very weak CPU to push 100 gig. And the reason is because the hypervisor is not doing anything that is related to the network. Rocky is copying memory directly to the NIC side.
Okay, cool.
You mentioned earlier that you thought 25 gigs were the future. Why was that?
Future, you said?
You said 25 gigs was the new 10 gig.
Yeah.
You did elaborate.
Okay. So yeah, I had a slide about showing basically why. The question is why using 10 gig today? If you are building a new server, new data center, or you are expanding your data center, and you're anyway buying good servers, and you are putting a NIC there, it probably is Mellanox NICs. We are kind of 90% of the NIC. We are selling 90% of the NICs all over the world, which is above 10 gig. And basically, what I'm saying is that you can have the same form factor, which is the SFP. It looks the same thing. It's called SFP28, but it looks the same way. And you can connect it to your NIC and have 25 gig running there instead of 10 gig. And I show some examples of how it can help you. For example, if you have very fast storage, NVMe, then you will need, for one VME, 3 links of 10 gig to make sure that your network is not a bottleneck. But you can replace 3 NICs with 1, which is 25, and have the same effect. Also, in general, faster network means you can do faster migration, and all the NVMe story will be easier for you, because we saw at the beginning that you can utilize your network very, very fast if you are moving to faster storage. So 25 is just, it looks the same physically. It looks the same as 10 gig, and you are getting more bandwidth from it. More questions? Good. Thank you very much, guys, for your time.